At 2:45 p.m. on May 6, 2010, the U.S. stock market basically just broke.
Yeah, it really did.
I mean, over the course of about 36 minutes, $1 trillion in market value just simply vanished.
Just completely evaporated. You had blue chip companies, the bedrock of the global economy, suddenly trading at a penny a share.
Right. And then other stocks were trading at like $100,000 a share.
Yeah.
Algorithms were firing blindly. Liquidity just dried up.
And human traders were just staring at their screens in absolute paralyzed silence.
Yeah, exactly. And then almost as quickly as the chaos erupted, the market just corrected itself. The prices snapped back. That $1 trillion reappeared.
Which is still terrifying to think about.
It is. It was the flash crash. And when the dust settled, regulators and analysts spent months trying to reconstruct exactly what happened. They looked at order flows, spoofing algorithms, macro indicators, you name it.
But what that day really exposed, in the most visceral way possible for you, the listener, is the sheer, untamed chaos lurking just beneath the surface of our financial systems.
We like to pretend the market is this rational machine, right? A perfectly efficient pricer of information.
But fundamentally, it is a system driven by millions of irrational decisions, breaking news, algorithmic feedback loops, totally unpredictable global shocks.
It's just perpetual, localized chaos.
And the paradox of modern finance is that we have built an entire global infrastructure. I'm talking pensions, derivatives markets, sovereign debt on top of this chaos.
You can't just throw your hands up and say, well, it's unpredictable.
No, you have to price the risk. You have to measure the uncertainty, which means you are faced with a seemingly impossible task.
Which is writing a rigid mathematical rule book for a system that actively defies rules.
Exactly.
Okay, let's unpack this, because that contradiction is exactly what we are dissecting today on this deep dive.
It's a fascinating topic.
It really is. We're looking at the architecture of quantitative finance. We're getting into the actual mechanics of how quants, risk managers, and financial engineers mathematically simulate this chaos.
Right, because we aren't looking at basic supply and demand charts today.
No, we are looking at the heavy machinery. We are looking at a document from an advanced certificate in quantitative finance course, specifically focusing on simulating and manipulating stochastic differential equations.
Which is quite a mouthful.
It is. But basically, this is the language of things that change randomly over time.
Yeah.
It's how Wall Street attempts to put a leash on pure, unadulterated randomness.
And it is a language that requires a complete shift in how you think about mathematics, because standard math, the kind of calculus designed to map the orbit of planet.
Or the trajectory of a cannonball.
Right. That math assumes a smooth, continuous, predictable universe.
But when you are dealing with a financial asset, you have to fundamentally hardwire uncertainty into the equation itself.
You really do. You have to build the anatomy of a random walk from the ground up.
So before we can simulate a complex portfolio for you guys, we had to understand that basic anatomy. Any stochastic differential equation, or SDE, essentially splits every movement in the market into two distinct warring forces.
Right. There is a deterministic part and there's a random part.
Let's break those down.
So the deterministic part is the signal. It's the predictable drift or the growth rate over a tiny slice of time.
Like the macro environment.
Exactly. Inflation trends, demographic shifts, long-term technological adoption. These things exert a steady directional pull on an asset's price.
So if you have a bond with a fixed yield, its growth is almost entirely deterministic.
It marches forward predictably. And in the equity world, you can think of this as the expected return based on the underlying fundamentals of the business.
But obviously, a stock doesn't just draw a smooth diagonal line up and to the right.
No, it definitely doesn't.
Which brings us to the second force, the diffusion, the volatility.
This is the noise. This is the high-frequency trading algorithm reacting to a misinterpreted headline. This is the sudden geopolitical shock.
Mathematically, this is modeled as a continuous series of random shocks, essentially a Brownian motion.
It's a barrage of unpredictable impacts, drawn from a normal distribution, just bombarding the asset price every single microsecond.
And the tension between those two forces is what defines the market. The SDE just formalizes this.
It states that any change in an asset's price is the sum of its predictable drift and its unpredictable diffusion.
The drift is scaled by time. The longer you wait, the more the underlying fundamentals assert themselves.
But the diffusion is scaled by volatility, a coefficient that dictates just how violent those random shocks are for this specific asset.
I always think of this dynamic like walking a highly energetic, very easily distracted dog through a massive park.
Oh, that's a perfect analogy.
Right, so you, the owner, represent the drift. You have a destination. You are walking at a steady, purposeful pace toward the park exit.
And if it were just up to you, your path would be a perfectly straight, deterministic line.
Exactly. But the dog represents the diffusion. The dog does not care about the exit.
Not at all. It is darting erratically side to side, lunging at a squirrel, stopping abruptly to sniff a tree.
Suddenly sprinting forward, then doubling back.
Right. Now, if you are a quant and you want to mathematically map the actual combined path of the dog...
Like the physical footprint left in the mud.
Yes. You can't just map your straight line, and you can't just map the dog's random jerks. You need an equation that continuously adds the two together.
Because the dog's position at any given millisecond is a product of your steady forward pull and its own violently random sideways movements.
And that combined path is the stochastic differential equation in action.
It's a great visualization because it highlights the continuity of the chaos. The dog never actually walks in a straight line.
Not even for a fraction of a second. If you zoom in on the dog's path, it remains infinitely jagged.
And this brings us to how quants specifically apply this to equities. Because the standard model for this, the absolute workhorse of modern financial mathematics, is geometric Brownian motion.
Also known as exponential Brownian motion.
Right, and the crucial distinction with geometric Brownian motion compared to just a standard random walk is that both the drift and the diffusion aren't fixed numbers.
No, they are dynamically scaled by the current price of the asset itself.
Why is that specific structural choice so vital for modeling the stock market?
Because it reflects the reality of compounding and proportional returns. I mean, think about it. If you have a stock trading at $10 and it experiences a 1% random shock, it moves by 10 cents.
Okay, sure.
But if that company grows massively over a decade and the stock is now trading at $1,000, a 1% shock is $10.
Wow, right. The absolute magnitude of the volatility scales directly with the price of the asset.
Exactly. And the same applies to the drift. A 10% annual return on a $10 stock is very different in absolute terms than a 10% return on a $1,000 stock.
It's an acknowledgement that investors think in percentages, not absolute dollars.
Precisely. If you modeled a stock with a constant absolute volatility, a $1,000 stock would look essentially frozen, while a $5 stock would be whipping around wildly.
Geometric Brownian motion fixes that by anchoring the chaos to the current valuation.
Furthermore, it inherently prevents the asset price from ever dropping below zero.
Oh, because if the price approaches zero, the scaling factor approaches zero.
Yes, which dampens both the downward drift and the downward volatility. In the real world, a stock price can't be negative. Limited liability ensures the worst you can do is lose your entire investment, hitting exactly zero.
Geometric Brownian motion captures that boundary condition naturally.
It really is an elegant baseline.
So we have this baseline. We have a mathematical representation of the dog on the leash, scaled for a blue-chip tech stock. But here's where the entire framework threatens to collapse on itself.
It really does.
Because having the equation is only step one. The whole point of being a quantitative analyst is manipulating these equations. You want to calculate derivatives, you want to hedge portfolios.
You want to track how the price of an options contract shifts as the underlying stock twitches.
Right, which means you need to do calculus.
You do, but the moment you try to apply traditional calculus to pure randomness, the machinery breaks.
It just shatters. The rules we learned in university, the calculus of Newton and Leibniz, they rely entirely on smoothness.
They rely on the concept of limits. The foundational idea of traditional calculus is that if you zoom in close enough on any curve, no matter how complex, it eventually looks like a straight line.
Right. You can find the tangent. You can measure the instantaneous rate of change.
But a random walk doesn't behave like that. Because the dog is acting purely randomly at every infinitesimally small fraction of a second, the path is fractal.
No matter how deep you zoom in, it remains infinitely jagged.
There is no straight line. There is no smooth derivative.
See, if I'm looking at how a derivative moves with the underlying asset, my immediate instinct is to just use standard mathematical tools we've had for centuries.
Like a Taylor series expansion.
Yeah, Taylor series. It's the classic way to approximate a complex function by breaking it down into its first derivative, its second derivative, and so on. Why can't we just use a Taylor series and ignore the fact that the path is jagged?
To understand why the old tools fail, we have to look at how a Taylor series handles time.
Okay.
In a deterministic, smooth world, when you take a tiny step forward in time, a fraction of a millisecond, that time step is small, If you square that time step, the resulting number becomes so unimaginably microscopic that it effectively vanishes.
It becomes a mathematical ghost.
Exactly. You can safely throw it in the garbage. That's why standard calculus usually only cares about the first-order terms.
That makes total sense. If my time step is 1,000th of a second, squaring it gives me 1/1,000,000th. For all practical engineering purposes, it's basically zero.
But the introduction of randomness fundamentally alters the scale of reality.
Okay, how so?
In stochastic calculus, we're dealing with a random variable, the diffusion term, the noise. And here is the bizarre, counterintuitive truth that forms the bedrock of quantitative finance.
I'm ready.
In the limit, the square of the random noise is exactly equal to the time step itself.
Wait, we need to pause and really look at that concept. The random noise squared equals time.
It is profound. Think about variance. The noise is drawn from a distribution where the variance scales linearly with time.
Okay.
So if you look at the random shock itself, its magnitude is proportional to the square root of time. And what happens if you square a square root?
You just get time.
Exactly. While the noise itself is completely unpredictable. I mean, it could be a massive positive shock or a massive negative shock. When you multiply it by itself, it crystallizes into a positive deterministic quantity.
The randomness annihilates itself through multiplication, leaving behind the steady march of the clock.
That's a poetic way to put it, but yeah. And because the squared noise equals the time step, it doesn't vanish into a microscopic fraction like a squared time step would.
It stays large enough to survive the equation.
It refuses to be ignored.
So all of those higher order terms in our Taylor series expansion, the second derivatives that we used to casually toss out because we assumed they were multiplied by a number too small to matter.
They suddenly come roaring back to life. They are resurrected by the volatility. And this realization is what gives birth to Ito's lemma. Kiyoshi Ito recognized that to do calculus on a random process, you have to formally include the second derivative.
So when you expand a function in this stochastic world, you don't just get the expected predictable change.
No, you are forced to add a massive new term that is entirely driven by the variance of the asset.
The math essentially says,
Yeah.
your function's value is changing not just because time is passing and not just because the underlying asset is drifting, but it is fundamentally altered by the sheer violence of the asset's movement.
Yes. That extra term, the second derivative multiplied by half the variance, is the mathematical footprint of the dog's erratic sniffing.
It doesn't exist in a smooth universe.
It only exists because the path is jagged.
Let's ground this in a real-world scenario, because Ito's lemma isn't just an abstract mathematical trick. It has massive implications for how money actually compounds.
It really does.
If we use Ito's lemma to solve the equation for a stock price over time, specifically by looking at the natural log of the stock price, which allows us to turn exponential compounding into simple linear addition, the resulting formula reveals something incredibly important about risk.
What's fascinating here is when you run the calculus, taking the first and second derivatives of the log function and plugging them into Ito's lemma, you get an exact solution for the future stock price.
And what does that equation look like?
The equation dictates that the stock price equals the initial price multiplied by an exponential growth factor. But that growth factor is not just the expected return.
Right.
It is the expected return minus 1/2 of the variance.
Wait, the expected return minus 1/2 the variance? So the math actually proves that volatility actively, mechanically drags down your growth rate.
This is the phenomenon of volatility drag, and it is crucial for any investor listening to understand. People often confuse average returns with compound annual growth rates.
Right.
If I offer you an investment that goes up 50% one year and down 50% the next, your average arithmetic return is 0. You might think you break even.
But the reality is catastrophic. Let's walk through that. If I start with $100 and it goes up 50%, I have 150.
Correct.
But if that 150 then drops by 50%, I don't go back to 100. Half of 150 is 75. I drop to $75.
You have lost 25% of your wealth, even though the average return was technically 0.
That destruction of capital is volatility drag.
The more violent the swings, the more capital is destroyed by the mathematics of compounding. Ito's lemma captures this perfectly by literally subtracting half the variance from your growth exponent.
So the more erratic the dog on the leash, the more energy is wasted moving side to side, and the slower your actual forward progress toward the exit of the park becomes.
This is exactly why leveraged ETFs decay over time.
Oh, that makes so much sense. If you buy an ETF that promises 3 times the daily return of the S&P 500, the volatility is amplified immensely.
Huge amplification. And over a long period of choppy, sideways trading, that amplified variance will eat the portfolio alive through volatility drag.
Even if the underlying index ends up exactly where it started.
Exactly. Ito's lemma is the inescapable gravitational force of risk. It proves that volatility isn't just a measure of emotional discomfort for an investor. It is a tangible mathematical friction that erodes compound growth.
So geometric Brownian motion and Ito's lemma give us a remarkably robust way to model equities. We have a system that accounts for compounding returns, proportional volatility, and the mathematical drag of that volatility.
And crucially, it models an asset that has no theoretical ceiling. A stock can theoretically compound infinitely.
But if we expand our view of the financial ecosystem, we quickly realize that a huge portion of the global market doesn't behave like equities at all.
The largest markets in the world are fixed income markets: sovereign debt, corporate bonds, mortgage-backed securities.
And the bedrock of all those markets is the interest rate. You cannot model an interest rate using geometric Brownian motion.
Because an interest rate can't compound to infinity.
Right. If the federal funds rate hits 500%, the entire global economy vaporizes. The currency becomes meaningless.
Interest rates are fundamentally bound by the gravitational pull of macroeconomic reality.
They require a different architecture, a different stochastic differential equation, which brings us to models specifically designed for interest rates, the most foundational of which is the Vasich model.
Also known mathematically as the Ornstein-Uhlenbeck process.
When you look at the SDE for the Vasicek model, the diffusion part, the random noise, the volatility looks very similar. The dog is still darting around.
But the deterministic part, the drift, is radically redesigned. It introduces 2 new parameters: a reversion rate and a long-term mean.
So in this model, the drift isn't just a constant push forward. The drift is a corrective force.
It's the mathematical engine of mean reversion.
I think the best way to conceptualize this is a rubber band analogy. A stock price in geometric Brownian motion is like a helium balloon. If you let it go, and the wind is blowing up, it just drifts higher and higher into the stratosphere.
There's nothing pulling it back down other than random downdrafts.
But an interest rate in the Vasicek model is attached to a thick, heavy-duty rubber band, and that rubber band is anchored securely to a post driven deep into the ground.
And that post is the long-term historical average rate.
Right. And the thickness, the tension of that rubber band is the reversion rate.
Let's look at the mechanics of the equation. It calculates the difference between the long-term average and the current rate.
Okay, so if the current interest rate spikes dramatically, let's say a central bank panics and hikes rates to combat sudden inflation, the current rate is now much higher than the historical average.
Which means the difference between them becomes a negative number. The equation essentially reads that negative number and says the rate is too high.
As a result, the entire predictable drift term becomes negative.
The math actively starts pulling the rate back down. The rubber band has been stretched tight, and the kinetic energy is yanking the rate back toward the anchor.
Conversely, if the economy crashes and central banks slash rates to near zero, dropping well below the historical average, that difference becomes positive.
The drift term becomes positive. The rubber band is stretched in the opposite direction, and it begins pulling the rate back up.
Now, the random volatility is still there. The noise is constantly trying to knock the rate around, creating local chaos.
But the drift is no longer a passive current. It is an active, aggressive, restorative force.
And we can see why this is so accurate for macroeconomics. That restorative force isn't just a mathematical abstraction. It represents real-world central bank policy and economic gravity.
High interest rates choke off borrowing, cool down the economy, reduce inflation, and eventually force central banks to lower rates again.
And low interest rates stimulate borrowing, heat up the economy, spark inflation, and eventually force central banks to raise rates. The economy naturally oscillates.
The Vasicek model hardwires that macroeconomic oscillation directly into the SDE.
So, to actually solve this equation, to figure out the exact path of the interest rate over time, quants use a technique called integration by parts.
They isolate the difference between the current rate and the mean and integrate it over time.
The calculus gets complex, but the output is beautifully intuitive. The final solution includes an exponential decay term.
And what that term does is mathematically guarantee that the impact of wherever the rate started, the initial conditions slowly dies out over time.
If you start with incredibly high rates today, That fact matters a lot for tomorrow, a little less for next year, and almost not at all for a decade from now.
Over a long enough timeline, the initial chaos fades and the pull of the historical average dominates.
It's a system with memory, but a fading memory. Now, we've outlined two incredibly powerful models. We have the log normal balloon floating away for equities and the rubber band snapping back for interest rates.
But so far, our entire conversation has been focused on a single path. We're simulating one dog walking through the park.
We are mapping one specific realized future. But if you are managing a multi-billion-dollar quantitative hedge fund, you don't care about just one possible future.
A single path is practically useless for risk management because you don't know which path reality is actually going to take.
You don't want a crystal ball that shows you one specific outcome. You want a radar screen that shows you the probability of all possible outcomes.
You want to know the odds. What is the precise probability that this asset will be trading exactly between $110 and $115 6 months from today?
To answer that, we have to move away from simulating individual paths and move into the realm of partial differential equations. We're talking about transition probability density functions.
This is a massive leap in abstraction, but it's where the real power of quantitative finance lies. Instead of tracking a single price point moving through time, we are tracking a fluid.
We are tracking a probability density that diffuses across space and time.
So, this is literally asking, what is the probability of the variable being in a certain range at a future time, given that it started at a specific value at current time?
The core question is, given that we know exactly where the asset is right now today, in the present moment, how does the probability of its future location spread out as we look further and further ahead?
To calculate that spreading, quants use the Fokker-Planck equation, also known as the forward-Kolmogorov equation. It uses partial derivatives to model how probability flows.
I love visualizing this as a physical landscape. Let's use the log normal model for a stock. At this exact second, times zero, there is absolutely zero uncertainty about the stock price.
You can look at your terminal and see it is exactly $100.
So on our probability landscape, the surface is completely flat, 0% everywhere, except for one infinitely sharp, impossibly tall spike right at $100. It is a spike of absolute 100% certainty.
But the moment you start moving the clock forward, even by a minute, an hour, a day, the Fokker-Planck equation activates.
The continuous bombardment of random noise, the volatility, acts like erosion on that spike.
It starts to batter it down. The spike melts, it flattens out, and the probability begins to bleed outward into the surrounding prices.
It transforms from a sharp spike into a narrow hill and then into a broader mound. The peak of the mound might drift to the right, following the expected growth rate, but the base of the mound gets wider and wider.
This widening represents growing uncertainty. The further into the future you look, the more time the volatility has had to scatter the possibilities.
A year from now, the probability distribution might be a massive, sprawling, gentle hill, covering prices from $50 to $200.
It's essentially the thermodynamics of risk. The Fokker-Planck equation is actually deeply related to the heat equation in physics, which describes how heat dissipates through a metal block over time.
In finance, we're watching certainty dissipate into uncertainty.
Exactly.
And this brings up a profound question about the ultimate fate of these models. What happens if we run the clock forward forever? If we let time approach infinity, does this probability landscape eventually settle down into a permanent shape? Does the fluid stop flowing?
The answer depends entirely on which of our two models we are observing. This is the concept of a steady-state distribution, and it highlights the fundamental difference between equities and interest rates.
Let's look at the Vasicek model first, the interest rate with the rubber band.
In that model, the volatility is trying to spread the probability outward, flattening the hill, but the rubber band, the mean reversion, is constantly pushing back.
It is pulling the probability toward the center, toward the historical average.
Exactly. You have two opposing forces. The diffusion is trying to maximize entropy, spreading things out. The drift is trying to minimize it, pulling things in.
And as time approaches infinity, these two forces reach a perfect equilibrium. The Vasicek probability density function stops changing.
It settles into a permanent, beautiful, unmoving, normal distribution, a perfect bell curve.
The mean of that permanent bell curve is exactly anchored on the historical average rate. And the standard deviation, the width of the bell curve, locks into a permanent ratio.
It becomes the volatility divided by the square root of twice the reversion rate. The chaotic energy is perfectly contained by the tension of the rubber band.
It's a closed, stable system. But if we switch back to the log-normal model geometric Brownian motion for a stock price, there is no equilibrium.
Because there is no rubber band. There's just the drift pushing it higher and the volatility spreading it wider.
The math dictates that a log-normal random walk has no steady-state distribution.
If you let it run to infinity, the probability hill just keeps flattening and stretching endlessly. The uncertainty becomes absolute.
In the extreme long term, the probability mass either escapes to infinity or decays asymptotically towards zero. There is no stable resting place for a perfectly unfettered equity.
That is the forward equation pushing probability into the unknown future. But quants also use the backward Kolmogorov equation.
Instead of using derivatives regarding the future state, the backward equation uses derivatives regarding the current state. Why would you run the thermodynamics of risk in reverse?
It seems counterintuitive until you think about pricing derivatives, specifically options.
Okay, give me an example.
Let's say you have a complex options contract that pays out $1 million if a stock is above $150 on December 31st, and nothing if it's below.
The final state is completely known. On December 31st, the payoff profile is rigid and certain.
But you need to know what that contract is worth today.
Precisely.
The backward equation takes that rigid future certainty, the payoff condition, and flows it backward through time, subjecting it to the eroding force of volatility in reverse.
It answers the question. Given this specific required outcome in the future, what is the probability landscape of initial starting positions that would lead me there?
By pulling the future boundary condition back to the present moment, quants can assign an exact, fair present value to the derivative. It is arguably the most important mathematical maneuver in all of derivatives pricing.
It's reverse engineering destiny.
It really is.
We've spent a lot of time in the abstract realm here. We're talking about continuous time, infinite futures, fluid dynamics of probability, and smooth curves. But we have to crash back down to reality.
Because ultimately, quants don't trade equations on a whiteboard, they build simulations on computer servers.
And computers, for all their processing power, are fundamentally incapable of understanding continuous time.
A computer operates on a clock cycle. It moves in discrete, blocky steps. It cannot comprehend dt, an infinitesimally small slice of time.
It can only process delta t, a fixed, measurable chunk. It could be a day, an hour, or a millisecond, but it has a rigid boundary.
So the massive engineering challenge is, how do you translate continuous stochastic calculus into a discrete recipe that a computer can actually execute without breaking the mathematics?
The standard bridge between those two worlds is the Euler method. It's an algorithm that allows us to approximate the continuous SDE in distinct iterative steps.
It essentially lets you build a stock market inside a spreadsheet or a Python script.
The transformation is relatively straightforward on the surface. You take our continuous equation, ds, and you turn it into a step-by-step formula.
The price of the asset at the next step equals the current price, plus the expected drift over the time step, plus the random shock over the time step.
But there's a massive, incredibly subtle trap hidden in that translation. If you just multiply the drift by the time step, and then multiply the random noise by the time step, your simulation will completely implode. The volatility will be drastically understated.
And the reason goes all the way back to the core weirdness of Ito's lemma. Remember the fundamental rule. The square of the random noise equals the time step.
Right. So if you isolate the random noise by taking the square root of both sides, the random noise must equal the square root of the time step.
Exactly. When you build the discrete recipe for the computer, the random number generator is spitting out a standard normal variable. To scale that variable correctly so that it accurately mimics Brownian motion, you must multiply it by the square root of the time step.
It's so easy to overlook. You think, well, the drift is scaled by time, so the volatility should be scaled by time.
But because volatility is rooted in variance, and variance scales linearly with time, standard deviation, which is what we are actually simulating, must scale with the square root of time.
If you miss that square root, your daily volatility will be off by a massive factor compared to your annual volatility. The entire risk model will be hallucinating a dangerously calm market.
Here's where it gets really interesting. Let's actually walk through what the Euler method looks like in practice, because seeing the mechanical steps demystifies so much of what happens on a trading floor. This is literally the foundational loop of a Monte Carlo simulation.
Okay, let's set the parameters. We start with an asset priced at exactly $100. We assume an annual expected growth rate of 10%.
We assume an annual volatility of 20%, and we decide our time step is going to be roughly 3 days, which mathematically is a delta of 0.01 years.
Step 1. The computer calculates the deterministic drift, 10% of $100, multiplied by our tiny time step of 0.01. That gives us a tiny upward push.
Step 2. The chaos engine kicks in. The computer needs a random shock. It pulls a random number from a standard normal distribution. Let's say the random number generator spits out a positive 0.12.
Now we assemble the pieces. We take the $100, we add the tiny deterministic drift, and then we add the shock, our 20% volatility, multiplied by the random 0.12, multiplied by the square root of our time step. The square root of 0.01 is 0.1.
The computer crunches the arithmetic. The random shock was positive, and it overwhelmed the tiny drift. The new simulated price for step 1 is $100.34. The stock ticked up.
Now the loop resets, step 3. The computer takes that new price, 100.34, and uses it as the baseline for the next calculation. The drift is recalculated based on the new price.
The random number generator fires again. This time it spits out a negative number, negative 0.25.
We run the formula again. The negative shock drags the price down. The new output is 99.94. The stock ticked down.
And you just repeat this loop. If you drag that formula down 10,000 rows in Excel or run a loop in Python, you have just generated one completely mathematically rigorous possible future for that asset over years of trading.
You have simulated one path of the dog.
But again, one path is useless. To actually price an option or measure value at risk, a bank's server farm will run that identical loop 10 million times, generating 10 million distinct diverging paths.
They will look at the final distribution of all those paths to understand the true probability landscape. That is the essence of Monte Carlo simulation.
But inside that massive Monte Carlo engine, there is a severe bottleneck. And it's something we casually glossed over in our step-by-step walkthrough.
We said the computer pulls a random number from a standard normal distribution.
Right. We assume the computer just naturally knows how to produce a perfect bell curve of randomness.
But computers don't do that natively. A standard computer function like rand in Excel or a basic random library in Python generates uniformly distributed numbers. It spits out a decimal between 0 and 1.
And crucially, every single decimal has the exact same probability of appearing. A 0.99 is just as likely to appear as a 0.50, which is just as likely as a 0.01.
If you generate a million of those numbers and put them in a histogram, you don't get a bell curve. You get a completely flat rectangular brick. The distribution is uniform.
But our entire mathematical model, the Brownian motion, requires a normal distribution. It requires a bell curve.
We need numbers clustered tightly around 0 to be highly common, representing the everyday hum of the market. And we need extreme numbers, the massive tail events, to be incredibly rare.
So the quantitative engineering challenge is, how do you mold a flat, uniform brick of data into an elegant, curved bell?
You have to translate the randomness. The most rigorous way to do this is called the inverse transform method. It uses the inverse cumulative distribution function.
To visualize this, imagine a graph. The vertical y-axis represents the raw, uniform output from your basic RAND function percentages from 0 to 1. The horizontal x-axis represents the final bell curve numbers you actually want.
Drawing the inverse CDF creates a very specific S-shaped curve across the graph.
It's steep in the middle and flat at the extreme top and bottom.
Exactly. So the computer generates a uniform number, say 0.50. You trace a horizontal line from 0.50 on the y-axis over to the S-curve and then drop straight down to the x-axis. It lands exactly on 0.
Now imagine the computer generates a 0.99. You trace that horizontal line across. Because the S-curve is so flat at the top, that line travels very far to the right before hitting the curve.
When you drop down to the x-axis, you land on a huge positive number, maybe a 2.5.
Because the curve is steep in the middle, a huge chunk of the uniform percentages get funneled directly into the center, clustering around 0.
Because the curve is flat at the edges, only the very extreme percentages get mapped to the tails. It's a brilliant mechanical funnel that forces flat randomness into a perfect bell curve.
It is mathematically flawless. But in the real world of quantitative finance, it has a fatal flaw: computational intensity.
But what if I want to run millions of these and my computer is lagging?
Calculating the inverse cumulative distribution function for every single step of a 10 million path Monte Carlo simulation requires massive processing power.
It involves calculating complex approximations of integrals. If you are a high-frequency trading firm or a bank trying to run overnight risk reports on millions of derivative positions, those floating point operations add up.
Your server fans are screaming, the simulation is too slow.
Which brings us to one of my absolute favorite pieces of pragmatic engineering in finance, the hacker's trick.
When quants need speed over absolute pristine mathematical perfection, they abandon the inverse CDF. They use a radically simpler method to generate a bell curve.
It sounds almost laughably basic. To get a single, normally distributed random number, you simply generate 12 uniform random numbers. You add them all together, and then you subtract 6.
That is the entire formula. It sounds like literal witchcraft. Why does adding flat bricks together somehow forge a curved bell?
It's not magic. It is the raw power of the central limit theorem. This theorem is arguably the most important concept in probability.
It states that if you take a large number of independent random variables and sum them together, the distribution of that sum will naturally converge into a normal distribution, regardless of what shape the variables started as.
Even if they start as completely flat, uniform lines, the intuition behind this is fascinating.
If you roll one six-sided die, the distribution is flat. You have an equal 1 in 6 chance of rolling any number.
But if you roll 2 dice and add them together, the distribution peaks in the middle. Rolling a 7 is highly probable because there are many combinations that get you there: 3 and 4, 5 and 2, 6 and 1.
Rolling a 2 or a 12 is rare because there is only one combination for each.
As you add more and more independent uniform variables together, the extremes become exponentially less likely.
To get the absolute maximum possible score from 12 RAND functions, all 12 would have to independently roll a perfect 1.0. The odds of that happening are microscopic.
But getting a sum right in the middle around 6.0 is incredibly easy because high rolls constantly cancel out low rolls. The middle bulges upward, the tails thin out, and the bell curve emerges organically.
So why exactly 12? Why not 10 or 50?
12 is the perfect pragmatic compromise. Mathematically, the more variables you add, the more perfect the normal distribution becomes, especially out in the extreme tails.
But adding 50 variables takes more processing power. 12 happens to be the mathematical sweet spot where the resulting distribution is practically indistinguishable from a true bell curve for most simulation purposes. But the computation is blindingly fast.
It relies purely on basic addition, which computer processors can execute at light speed.
And the subtract 6 part is just shifting the graph. Since a standard RAND averages 0.5, 12 of them average 6. Subtracting 6 shifts the center of the bell curve down, so it rests perfectly over 0, giving us the mean of 0 that Brownian motion requires.
Furthermore, the variance of a standard uniform distribution is mathematically 1/12. If you add 12 of them together, the variances sum up. 12 times 1/12 equals exactly 1.
So without any complex scaling, this trick inherently produces a standard deviation of 1. You get a mean of 0, a standard deviation of 1, shaped like a perfect bell, all using elementary school arithmetic. It is a masterpiece of optimization.
It is brilliant. But as we marvel at the ingenuity of these localized hacks and single-asset models, we have to pull back and look at the macro reality of a trading floor.
Up to this point, our entire discussion has essentially modeled an asset in a vacuum. A single stock, a single interest rate.
The dogs are walking through the park entirely alone.
Exactly. But financial markets are not vacuums. They are infinitely complex, tangled webs. A hedge fund portfolio doesn't consist of one asset, it consists of thousands.
And crucially, those assets move together. If the technology sector suffers a massive algorithmic flash crash, Apple and Microsoft do not experience independent, isolated random walks.
They crash simultaneously. They are correlated.
This is the realm of portfolio theory and systemic risk. If you build a massive Monte Carlo simulation for a bank's entire trading book, and you mistakenly assume all the random variables are independent, meaning you use unlinked random number generators for every single stock and bond, your simulation is going to be dangerously flawed.
Because it will assume that when the tech sector crashes, maybe the financial sector will randomly soar and offset the losses. It will assume the chaos cancels itself out.
It vastly underestimates tail risk. In reality, during a true market panic, correlations spike toward 1. Everything sells off together.
If your simulation cannot mathematically bind the random walks of different assets together, it is worse than useless. It is actively deceptive.
So the final, and perhaps most critical challenge we need to decode is, how do we simulate correlated randomness? How do we program the chaos so that the dogs in the park influence each other's erratic behavior?
We need two random variables, let's call them phi1 and phi2, representing the daily shocks to Microsoft and Apple. And we need them to share a very specific mathematical correlation, denoted by the Greek letter rho.
If rho is 1, they move in absolute perfect lockstep. If rho is 0, they are entirely independent. If rho is 0.7, they move together most of the time, but with distinct individual variations.
The mathematical process to achieve this is essentially a simplified version of Cholesky decomposition.
I always picture this process like mixing paint. Imagine you are a landscape painter. You need two distinct colors for the sky and the ocean. You need them to look different, but you want them to be aesthetically harmonious. They need a shared visual DNA.
To achieve that, you don't just pick two random colors off the shelf. You start with primary unmixed bases. In our mathematical world, these bases are two completely independent, perfectly standard, normal, random variables generated by the computer.
Pure, uncorrelated noise. Let's call them epsilon 1 and epsilon 2.
To create your two correlated colors, you keep the first one pure. Color 1, the sky, is just the pure primary base, so phi1 simply equals epsilon 1. It is an unaltered random walk.
But for color 2, the ocean, you don't just use the second pure base. You blend it. You take the second independent variable, epsilon 2, but you inject a very specific calculated ratio of the first variable, epsilon 1.
You mix the sky into the ocean to create the correlation.
The mathematical recipe for that blending is elegant. It uses a linear combination. Phi2 equals the correlation, rho, multiplied by epsilon 1 plus the square root of 1 minus rho squared multiplied by epsilon 2.
The correlation coefficient rho is acting exactly like the mixing ratio for the paint. If rho is high, say 0.9, you are dumping a massive amount of the first variable into the second. They will move almost identically.
If rho is low, say 0.1, you are only adding a tiny drop, and they will remain largely independent.
And the incredible thing is that we can prove this works using basic statistical rules. The most important rule here is that weighted sums of normally distributed numbers are themselves normally distributed.
Because we are just adding fractions of bell curves together, phi2 remains a perfect bell curve. It doesn't get distorted into some weird, unreadable shape.
Furthermore, the specific weights used in the formula rho and the square root of 1 minus rho squared are chosen intentionally to preserve the standard deviation.
If you calculate the variance of phi2 by squaring the equation, the math forces all the messy cross terms to behave. You're left with rho squared plus 1 minus rho squared, which perfectly equals 1. The variance remains untouched.
And when you check the correlation between the two new variables by calculating the expected value of phi1 multiplied by phi2, the completely independent parts mathematically cancel out to 0. The only thing left standing is exactly rho.
You have successfully forged two random walks that will dance together, intertwine, and crash together to the exact precise rhythm you specified.
When you expand this logic from 2 assets to a portfolio of 500 assets, utilizing full matrix algebra and Cholesky decomposition, you have the architecture for modern portfolio risk management.
You can simulate the entire global economy, complete with sector correlations, currency pegs, and supply chain dependencies, all driven by a massive, interconnected web of stochastic differential equations.
It is genuinely awe-inspiring when you step back and look at the entire edifice we've just explored.
So what does this all mean? We started with the sheer, unadulterated terror of a market crash, pure, unpredictable chaos. We built the fundamental anatomy of an SDE to dissect the difference between macroeconomic drift and microeconomic diffusion.
We pushed past the limitations of traditional mathematics and embraced the counterintuitive reality of Ito's lemma, where volatility itself becomes a physical drag on compounding wealth.
We contrasted the limitless, unanchored growth of equities in geometric Brownian motion with the heavy, mean-reverting macroeconomic gravity of the Watzlawick interest rate model.
We looked into the future using the fluid dynamics of the Fokker-Planck equation to map probability clouds, and we ran time in reverse using the backward equation to price derivatives today.
We translated all of this lofty, continuous math into the pragmatic, discrete reality of computer simulation using the Euler method. We learned how to forge perfect bell curves out of raw, uniform data using the central limit theorem.
And finally, we learned how to bind those random walks together to model systemic risks.
It is an incredibly sophisticated, highly structured toolkit. It represents decades of brilliant minds attempting to build a cognitive map of financial reality.
It provides an illusion of control over the chaos. But as we wrap up this deep dive, we have to confront the limits of that control. Because no matter how elegant the math is, no matter how perfectly the matrix algebra links the random walks, there is a fundamental assumption hardwired into the absolute basement of this entire architecture.
The assumption of normal randomness.
Exactly. Every single thing we discussed today relies on the assumption that market shocks fall into a bell curve.
We force our models to spit out normally distributed numbers. The math requires it. But the reality of human behavior, the reality of global markets, does not perfectly adhere to a bell curve.
This brings us to the concept of abnormal randomness, or what Nassim Taleb famously popularized as black swan events.
In a perfect, theoretically sound bell curve, the extreme tails are infinitesimally small. A market crash of 20% in a single day is, statistically speaking, under a normal distribution, an event so improbable that it shouldn't happen even once in the multi-billion-year lifespan of the universe.
Yet we experienced it in 1987. We saw massive multi-standard deviation breakdowns in 2008. We saw unprecedented volatility during the onset of the pandemic in 2020.
Human panic, cascading margin calls, and algorithmic feedback loops create fat tails extremes that are vastly more common in reality than they are in the mathematical models.
When a black swan hits, the correlations don't just act according to our precise paint mixing ratios. They all violently snap to 1.0. Everything crashes simultaneously, blowing right through the risk limits calculated by the backward Kolmogorov equation.
So the final thought we have to sit with is this. These SDEs, Ito's lemma, the Euler simulations, they are masterpieces of applied mathematics. They are essential for navigating the day-to-day weather of the markets.
But we can never forget that the map is not the territory. The math maps a reality that operates according to continuous, bounded rules. But the actual market is a complex human system capable of discontinuous, unbounded panic.
Are our incredibly complex quantitative models actually mapping the true reality of the world? Or are they merely mapping a mathematical reality that we are intellectually comfortable with? That is the ultimate question at the heart of quantitative finance. Thank you for joining us on this incredibly deep journey into the architecture of randomness. Keep questioning the numbers, keep exploring the chaos, and we'll see you next time on The Deep Dive.